Happy New Year.
So guys, Nathaniel got us thinking about this idea of the math of chemical equations, thermochemical. And it was, hey, if you make 0.45 moles, how much energy comes out? Guys, the question becomes this: where do those numbers come from? It was like negative 65.5 kilojoules per mole. Where do we get that number? How do we arrive at that number? And guys, there are two answers to this question. One is calorimetry, and one is Hess's law. Now guys, we are going to deal with these separately. Does that make sense in your head? Now make sense of this. Guys, today we're going to do Hess's law. Today we're going to do calorimetry. But guys, we're going to do it twice. In this class, we are going to do it the way they want you to know this for the AP test. In third period, we're going to do it the way they want you to know it in college. And that is going to lead us to the lab. So guys, what we're going to do is we're going to sort of allow our equation sheets to be the divider. So guys, if you grab your equation sheet, and if you turn to the page 4 side, where it says thermodynamics and electrochemistry, keep that as a reference. But guys, again, let's be really clear about this before we dig in. Today we are going to do calorimetry. Second period, the way the AP test wants it. Third period, much deeper, much better, but not part of the AP curriculum. But it is going to be how we do the lab. Does that make sense? Okay. So guys, with that said, where do we get started? And the idea is this. You don't need to write any of this down, but just let's be really clear. Guys, the question that we're asking is, where do these numbers come from? And again, the answer is this. We can get this data empirically. That is called calorimetry. We can also get this data through what's called Hess's law. That can happen one of two ways, through manipulation or through computation. What you're going to see is when I see you on Friday, we're going to talk about both of these. But guys, today we are going down the empirical way. What does empirical mean? Experimental evidence, and that's calorimetry. Got the idea? Here we go. So guys, in order to do this, we need to talk about two different, and you want to write this down. There are two different ways to deal with heat. And guys, you really need to write all of this down verbatim. So guys, the first is heat capacity. And guys, the words matter. Heat capacity is the amount of energy needed to raise a system's temperature 1 degree Celsius. And guys, obviously the term system is the important nugget, right? So you ready? Given the definition of heat capacity, what are the units for heat capacity?
Joules.
So joules, because joules is energy.
It would be joules over Celsius.
Exactly. Guys, the units are joules over degrees Celsius. Guys, let that rattle for a minute. The amount of energy needed to raise a system's temperature 1 degree Celsius. So it's joules over degrees Celsius. That leads us to the equation. So guys, the abbreviation for this is HC. The equation is this. Heat capacity, H sub C, is Q, which is energy, divided by delta T, which is change in temperature.
So if you were changing 1 degree, then it would just be energy. It would just be the joules.
but it would still be per degree Celsius.
Yeah, but
Yeah.
if you just have one,
Correct.
then it would just be divided by 1.
Yeah, so let's take that in another direction. You guys all caught up so you can think? Say you have a system and you dump 100 joules of energy into the system, and the temperature goes up 5 degrees. 100 joules, 5 degrees. What's the heat capacity of the system? 20 joules
per degree.
Does that make sense? So every 20 joules that we dump into the system, the temperature goes up 1 degree. Is that okay? Okay. This is not on the AP test. If you want to make note to yourself that this is not on the AP test, we've already established the units, joules per Celsius. Guys, this is not on the AP test. We're going to do a lot with it, but it's not on the AP test. You'll understand in a minute how the AP authors get away with this. But guys, this is not on the AP test. So what is on the AP? What do you need to know for the class? And guys, the answer is specific heat. So, guys, I just got to warn you. When you get to college, you will probably run into professors that will teach you this, but they're going to call specific heat capacity. And then it gets really confusing. So, guys, it is completely acceptable to call this just specific heat. But you may find that people will talk with you about specific heat capacity. Don't confuse that with this. Heat capacity is one thing, specific heat is another, even if you call it specific heat capacity. So what is it? And the answer is this. It's the amount of energy needed to raise 1 gram of a substance's temperature 1 degree Celsius. And again, guys, this is something that you want to write down verbatim. You good? So, guys, this is abbreviated C. I know, this is crazy. Trust me. We'll pull this together. You're not swimming in a bottomless sea. But guys, that was pretty good. Bottomless. Thank you. Guys, this is the equation for specific heat. Let's talk about it. The amount of energy, joules, to raise a gram. So there's got to be a mass component, 1 degree Celsius. So this is what the equation looks like. Q, which is energy. It's the amount of energy, Q. Is that too small? Can you guys read that okay? Okay. So guys, it's the amount of energy, Q, needed to raise 1 gram mass, temperature 1 degree Celsius. And then guys, C is actually the heat capacity, or the specific heat. It's a lowercase c. That's right.
So,
and it's no longer the speed of light.
So the units...
Yeah, that's where we're going. Is...
gram degrees Celsius over joules.
Flip it over. It's joules per gram Celsius degree. But guys, let's talk about why. I know that seems crazy, but one of the skills that you may or may not have developed is this. Oh, it's black. I'll just go with it. Q is equal to MC delta T. And guys, I got to tell you, when I was in high school and college, I learned the equation differently. I learned it M delta TC. Doesn't matter. So sometimes I'll write it wrong to you, but I'll do my best. So if we want to solve for C, what do we divide by? No. If we want to solve for C, we divide by M and delta T. So it's Q, energy, joules, mass, grams, change in temperature, degrees Celsius.
Oh.
Okay?
Is C is Q.
C is equal, so C is equal to Q divided by MT, delta T. So the units for C are the amount of energy, joules, to raise 1 gram of whatever the substance is, 1 degree Celsius. Does that make sense? Okay. Guys, this you need to know for the AP test, which tells us we're going to find it on the equation sheet, right? So let's find it. The first one on the equation sheet. And you'll notice that they give you, they call it specific heat capacity. Does that hurt us?
Yes.
A little?
There's nothing a little about it.
I know. It cuts to the core. But guys, you'll notice that they give us all of the units, or all of the abbreviations. You okay with that? Okay. Now, guys, I'm going to stretch you just a little bit. And now I do want to change colors. So, talking about specific heat. So, guys, let's go back to the definition. It is the amount of energy needed to raise 1 gram of a substance's temperature 1 degree Celsius. For some of you, that might be familiar. Do you know it? Like, what, does that make any, go ahead, Liam, what?
Calorie.
Yeah. Guys, this is actually the definition of a there's another C. This is actually the definition of a calorie. But if it's the calorie, what's the substance? Water. So guys, the specific heat, the C of water is 1 calorie. The specific heat of water is 1 calorie. But guys, we don't use calories in here, we use joules. And so the C for water is 4.18 joules per gram Celsius degree.
Doesn't water have a pretty high specific heat?
That's a freakishly high specific heat. Yeah, and I'd be interested to talk about that with you for a minute. This is strange, though. So this is last year's equation sheet. They took the value for the specific heat of water off of it. That's interesting. So guys, what that means is they'll give it to you on the test. They wouldn't ask you to memorize that value. But guys, we have a couple minutes and we can talk about this. So Sharp brought up a really interesting point. Guys, relatively, this specific heat is ridiculously high. Guys, the fact that it takes, let's call it 4 joules of energy to raise 1 gram of water's temperature 1 degree Celsius is ridiculously high. But guys, you understand life depends on it. What covers most of the earth? Water. And guys, water on the earth is a huge heat sink. And guys, if you don't understand what I'm talking about, you ever camp down in Moab in like July? Guys, during the day, the temperature gets up to like 100 and a billion degrees. But at night, you're freezing your butt off, right? Why? There's no water. And guys, because there's no water, the sun just shines down on the sand. And sand has a really low specific heat. And so all of that energy, joules, guys, has a huge impact on the temperature of the sand because it takes much less energy to change the temperature of sand's temperature a degree Celsius. So all of that energy causes the temperature of the sand to go through the roof, and it's hot. But then, guys, at night, the air becomes cooler. But the sand doesn't have a lot of energy to re-radiate into the air, and so it gets colder at night. So the range of temperatures is much greater in the desert.
So this works in reverse too? Like if If 1 gram of water decreases by a degree Celsius, it releases 4.18.
Exactly, and that's like, so for example, if you live in California on the coast, it's like the high temperature is 82 degrees, and the low temperature was 68 degrees. So guys, why doesn't it get cold in California at night? Because you got all that water to re-radiate its energy back into the air, right?
And you can't do work, so it has to do heat.
Stop it. But guys, what about this? Metals have really low specific heats. You want to experience that? Grab the leg of your table. Feels cold, right? Because guys, our bodies are largely made of water. And our bodies have relatively high specific heats. So as we dump energy into the, and guys, think about this. When does energy stop traveling between us and the table leg? When we're at the same temperature. But guys, the idea is that the specific heat of the leg is so low that it doesn't take much energy for these to come to the same temperature. But we experience this as cold because its specific heat is so low that energy just dumps really fast, the temperature becomes equal. But guys, we experience that as being cold because it has a low specific heat. Isn't that weird?
And so it's like it's sucking the heat away from it.
But it does it really fast because its specific heat is low and it heats up really quickly. Weird, right? You guys getting the idea behind this?
So theoretically,
Yeah.
the thing with the lowest, so with the highest specific heat,
Yeah.
would be like a perfect vacuum because it takes infinite energy to raise it.
Yeah. But here's the thing that's really interesting. There's a line in between. And so maybe the question then becomes, in general, what substances have the higher specific heats, even higher than water? And the answer is gases. It's really hard for gases to absorb energy. Why? Because they're so spread out. There's such and that's a gas, right? It's all spread out. Consequently, it's not a good absorber of energy. And so as a result, gases are good insulators.
If you take less and less gas, like if you lower the pressure, so there's less particles than it would get.
Sure, because think about what you're doing. If gas doesn't absorb energy because it's all spread out, if you can have less gas, it's more spread out, and it's a better insulator. So that's why right now in our homes, I don't know if you know this, our windows are double pane. They have an inside and an outside glass, and the stuff that's in the middle is argon. Why do they put the argon in there? Wouldn't it be better for it to just be a vacuum? And the answer is yeah, but the glass would shatter. So they have to have something in there to support the panes of glass, but they use argon because its specific heat is so stinking high that it doesn't conduct heat well. Isn't that interesting? You guys good on these ideas? All right, guys, here we go. Whew. I know that this is largely lost on you because we live in Utah County. But guys, what we're going to do for the rest of the day is talk about what is called coffee cup calorimetry. I know. Anywhere but Utah County, people would go, oh, I know what that is. So you can call it hot chocolate cup calorimetry if you choose. But guys, at the end of the day, this is an accepted term on the AP test, college, whatever. Coffee cup calorimetry is a thing. And guys, this is what we're going to do for the next 20 minutes, is we are going to talk about how coffee cup calorimetry works. And so guys, in order to do this, just watch. In order to do this, we need to understand what a coffee cup calorimeter is. Please don't draw this. We will together in a minute, but don't draw this. So guys, a coffee cup calorimeter, and just let me try this and see if this works. A coffee cup calorimeter is an isolated system. Those words have never crossed my mouth, but I wanted to try it. Does that make sense?
I don't believe you.
Right, but given what we taught, isolated means it's insulated. Is that landing at all?
Yeah.
Really? Because again, I've never. The word isolated is new to this new version of the book. It wasn't in the old book. So guys, talk with me about this. In the future, should I make that connection with isolated? It's not part of the AP curriculum. Or is it just enough to call it insulated? Either?
I think that isolated kind of helps you understand that it's meant to remove like matter and heat can't be correctly.
Okay, so maybe I'll keep it. Anyhow, so guys, these are the parts of a coffee cup calorimeter. You have a coffee cup. But guys, we tend to stack these coffee cups. We're going to go one step further, and we are going to put, oh, here's another Utah County term you won't know. Do you know what a koozie is?
Yeah.
Yeah.
Okay, so guys, in populations that consume a lot of beer, a beer koozie is actually a foam sleeve that fits around your beer can so it doesn't get warm.
They still hand those out here.
What's that?
They still hand those out here. Like I've been handing them like at like.
So what do you call it?
You put them over like your soda cans. Yeah.
A soda koozie. All right, here we go. But it can't be Coke. It is a 7-Up koozie.
I think that one got dummied out recently.
Are we done with that?
Yeah, we're done.
Thank goodness. I think it was Mitt Romney. Here we go. So, guys, what we're going to do is we're going to take a koozie and we are going to put a coffee cup inside of that. That actually provides a little bit of an air gap between there, which actually makes a better insulator. Then we are not going to put a fitted lid on this. Guys, a better insulator is cardboard. So we're going to put a piece of cardboard on top of this. Then we are not, wait a second. Take this under advisement. Okay, so we are going to penetrate the top of this with a thermometer. But guys, rather than allowing the thermometer to float free, what we're going to do is we're going to put a stopper, we're going to cut a slit in a one-hole stopper, and we're going to wrap it around the thermometer. And it holds fairly tight to the thermometer. That way, not only can we adjust its height and it won't fall, but it also sort of seals the hole where the penetration for the thermometer is. Then guys, the only other, I'm not sure. Some years we do this, and we need to stir it. Some years we take a piece of what's called nichrome wire, nickel chromium steel wire, and we go down with it, and then we make a horizontal loop that we put around our thermometer, and then we stir by lifting and dropping. I may not do that this year and have you use a magnetic stirring plate to stir.
I have always wanted to.
Eventually you will. It may not be Friday. Then guys, the only other thing you need to know is this has got water in it. This has got water in it. And that's a coffee cup calorimeter. You are going to build these on Friday and use them to study the energy that is released by acid-base neutralization reactions. Now the question is, how do they work? So guys, now we're going to draw one. I'm going to switch, maybe. Oops, hold on. I got to get rid of this. Gone. Okay. Goodbye. This, guys, is what you want to draw, and you want to leave a lot of space around this. I would encourage you to right shift it a little bit. And then, guys, we're going to go... Yeah. We're going to go cup. We're going to go lid. We're going to go water. We're going to go thermometer. And for now, let's just put a stirry bar down at the bottom.
There are the last 3 C's. I just realized: coffee cup, calorimetry, speed of light, and the news.
It all just came together.
We have all 7 of the C's.
Wait, so is the bottom thing the matter?
No, the bottom thing is, you can't tell what that is?
Sorry.
I'm actually a little hurt. Oh, shoot.
I bet your mind's not going to be much better.
No, so this is the... Oh, you've never seen one. This is the plastic bar that the stirring plate grabs a hold of and stirs. So it's the stirrer. It's actually more oblong.
Stir box.
Yeah, that's the stir bar.
We didn't learn it first term.
There's a chemistry YouTube channel I watch that uses those all the time.
Oh yeah? Yeah, they're wonderful. They work great. So guys, these are the questions that you need to be able to answer. What is our system? What is our surroundings? You need to be able to answer, what is coffee cup calorimetry useful for? You have got to be able to talk about the heat that is involved in this. And you've got to be able to talk about the enthalpies that are involved in this. Okay, so guys, before we dig into this, let's be absolutely clear. This is what you need to know for the test. This is only the tip of the iceberg for what we're going to do in lab. Clear? Okay, so guys, let's start answering these questions. And we are going to start by answering question number 3. What does that squiggly line represent? Water. So guys, the only thing that this is good for, don't write it down yet, the only thing that this is good for is chemistry that happens in water. But what do we call those things? Aqueous reactions.
That's why this is the chapter after the last one.
Hey, what? So guys, the only thing that this is good for is aqueous reactions. So then you're thinking, well, wait, not all reactions are aqueous reactions. How do we study those? And the answer is there's lots of different kinds of calorimeters. Guys, as you summarize chapter 5, right? Yeah, 5. You might have run into bomb calorimeters.
Yeah, those ones sounded really exciting, and then I read the description of it.
Yeah, they're not that exciting. But guys, they wrote bomb calorimetry out of the AP curriculum, so we don't go there anymore. If you'd like to dig into it more deeply, I'd be happy to explain it to you. We have a bomb calorimeter. We just don't do it anymore. But understand that bomb calorimetry actually allows you to study combustion reactions. Okay, so that's what this is good for. So now, guys, we've got to talk about our system, and we've got to talk about our surroundings. Guys, given your robust understanding of system and surroundings, you are going to recoil at what I'm about to tell you. I'm going to leave this offensive for now, and then we're going to fix it in third period. Okay? So, guys, what is our system? Our system is not the water.
It's the whole.
Our system are the reactants and the products of the chemistry that we're studying. In lab, your system will be sodium hydroxide and hydrochloric acid, and then the product, sodium acetate and water. And then the second time you do this, it will be acetic acid and sodium hydroxide, and then the sodium acetate and the water. So guys, your system are the reactants and the products, the atoms, the molecules. So guys, then the question becomes this, and this should not be okay with you. Guys, if we know what the system is, what's the surroundings? Everything else. But guys, that is not the way we do this in AP. Our surroundings is one thing and one thing only, and that's the water.
Is that because that's just the only thing that's like around, like that we're focusing on?
Let's talk about that in just a minute.
Is it because it's isolated?
No, but kind of. So, guys, let's now talk about heat. And let's just tell you right now, the reactions that we're going to study on Friday are both exothermic. So So acid-base neutralization reactions tend to be exothermic. So guys, let that sink into your mental picture a little bit. Our system are the reactants and products, the acid bases and the salt solutions, the products. And guys, it's exothermic. So which direction is heat flowing? Out of the system and into the surroundings. So guys, heat is flowing, so Q system is flowing into Q water. So guys, this is the oversimplification that we make for the AP curriculum that you guys, as I told you, are uncomfortable with and trying to explain. And Liam hopped in really intelligently, and he's like, is it because it's isolated? And Nora, you were talking about another explanation. What were you thinking?
Just because that's like the immediate, like that's the immediate surroundings. That's like nothing else could have not affect it, but nothing else is in the vicinity that we're looking at.
And I love the way you're talking about that, but I can feel even in the way you're saying this, you're justifying something, right? So guys, join me for a minute. Imagine that we dump acid and base into this cup. Which direction does energy go? Out. And guys, where does it go? It goes everywhere. Guys, it goes into the water. It goes into the air. It goes into the thermometer. It goes into the stirring bar. It goes into the cardboard. It even goes through the cardboard and through the styrofoam and out into the room. Guys, energy goes stinking everywhere. And how do we know this? Well, guys, imagine doing this. And we would never do this, but imagine that you mix the acid and the base in the thing. And then you stuck your finger in there. What's it going to feel like? Hot. But then if you come back a day later, what's it going to feel like? Room temperature.
And then your finger is just going to be gone.
Hold on a second. But guys, and actually it wouldn't because the salt solution is neutral. But,
Oh, yeah.
so guys, you understand the implications of this. Energy goes everywhere, and ultimately that energy goes into the room. And we know that that's true because given enough time, we would come back and this would be at room temperature. Does all of that make sense? Because you understand now all of your justifications are shot, right? It's not because it's isolated. It's not because the water is the only thing absorbing the energy. Guys, at the end of the day, this is bad science. It's oversimplified science. So guys, how will they handle this on the AP test? And they'll say something like this. 50 grams of solid sodium hydroxide is immersed in 100 milliliters of 1 molar hydrochloric acid. What is the delta H for this reaction, assuming that all of the energy goes into the water? It is a huge assumption. It is literally, in the true sense of the word, a gross assumption. It is inappropriate. But guys, that is the way that we do this for the AP test. We're going to fix it in third period. So guys, then the question becomes this. What does the math look like? So guys, draw this with me. So we understand that the heat that is lost by the system is the heat that is gained by the water. But guys, remember when we said that we can't directly measure energy? What evidence are we going to have that energy is being exchanged?
The water's going to heat up.
Water or cool down if it were endothermic, but in this case it's heating up. Guys, what we're looking at is the temperature change of the water. So guys, here's what we know. We drew, and this is where we're going to start talking about enthalpy. Guys, we drew this arrow. What does that arrow represent? The direction of flow for these reactions. But guys, this is what we actually know. I want to draw that a little smaller. I'm going to run out of space. So guys, Q for the system is equal to delta Q. Delta is equal to delta Q for the water. So what we're saying is this. All the energy that is lost by the reaction is gained by the water. We know that's an oversimplification. But we're going to roll with it. Just a second. But guys, here's the idea. Pretending that this is not an oversimplification, says who? Who says that all the energy lost by a system is gained by the surroundings?
The laws of thermodynamics.
The first law of thermodynamics. Guys, all the energy lost by the system is gained by the surroundings, but we're just calling the surroundings the water. But now, guys, watch what we can do. We have established that the water is going to change temperature. And at this point, we can do this. We can say that the energy that is gained by the system, because it is equal to the energy lost by the system is equal to the amount of energy gained by the water. But guys, we know this. Q is equal to MC delta T. So we can replace this with this, and MC delta T we can measure. We can measure the mass. We can measure the temperature change. But guys, the mass and the temperature change of what?
The water.
The water. And we know the specific heat of water to be 4.18 joules per gram per Celsius degree. So here's what we're going to do in lab. We're going to weigh the water. And we're going to measure the temperature change of the water. And by knowing the specific heat of the water, we then know the amount of energy that is gained by the water. Does that make sense? But now we know that that is equal to the energy lost by the system. But we flip the sign. Let me keep going for a second. Does this make sense? Okay, so now guys, we've got to turn this into enthalpy. And it goes like this. As a result of everything that we just talked about, here's what we're going to know. We're going to know Q. We're going to know the amount of energy that is lost by the system. Is that okay? But now guys, this. We need to turn this into an enthalpy of reaction. So let's talk about how to do it. Say it's our first reaction, so it's HCl plus NaOH yielding salt and water. Now guys, look at what we know. We know the amount of energy that the system gives away when that reaction happens. But what we can't do is just tag a delta H on the side of it and bring that number down here. Why doesn't that work?
You have to convert it into the right unit first.
Closer. Is why doesn't it work? Go ahead.
The energy lost isn't necessarily the change in heat, and
Actually, it is. So guys, why doesn't it work? Let's use a number. Just a round number. Let's say 1,000. So guys, what if the value for this was 1,000 kilojoules? How much sodium hydroxide and hydrochloric acid release 1,000 kilojoules of energy? How much? A mole of each. Yeah? So guys, if we take a mole of this and a mole of this, it releases 1,000 kilojoules. But guys, what if in the calorimeter we didn't use a mole? If in the calorimeter we didn't use a mole, say we use less than a mole, then how much energy will we report? Less than 1,000 kilojoules. So guys, in order to turn this into an enthalpy of reaction, here's what we've got to do. we've got to take this Q and divide it by the amount, let's say, of HCl. So what the number that we have is a Q per however much HCl we use. But what we need to do is turn this into a Q per mole of HCl. And guys, we'll talk about this more in third period, but that involves a dimensional analysis step. Okay, so guys, don't put anything away. This is where we're going to pick up third period, and we're going to fix these problems. Again, you do not have second period homework as a result of what we just did. The homework is going to come in third period. Take a break. We'll see you back. All right, so guys, this is just me shooting straight with you. This is probably going to be the most complicated thing you've ever thought through in your entire life. I understand that your butts are maybe now experiencing increased blood flow, but they've been pretty firmly planted in a seat, and now we're back. Guys, there's no other way to do this. And I'm just going to be straight with you. This is hard. Because it's not only challenging conceptually, it's also challenging mathematically. But then, guys, and this is a gut check for us. Some of us have developed patterns and flow in lab where we're just tight focused. But guys, thinking about the last lab that we did, there's also some of us that haven't developed that ability to focus and really be thinking about what we're doing. This is going to sort of tell you out. Because guys, when you do this lab on Friday, if you're not paying attention, all of your data is going to be bad. And I'm not going to let you copy another group's data. You'll be coming in and doing it over. So guys, this is really, and you guys understand, and we talk about this a lot. And actually it was neat. After the conversation that we had on Monday about, guys, some of you are just dropping off and I'm afraid you're going to get left behind. I had many people come and talk with me. And they're like, hey, I feel that. I agree with you. I'm feeling that in myself and I want to fix it. Interestingly, the people that have fallen off the most didn't come talk to me, but that's a whole other thing. But, guys, the thing that I heard from those of you that came and talked with me was, I know that you keep saying we're in process. And I believe that wholeheartedly, guys. But this is one of those milestones. This is one of those monuments in the desert that we sort of rally around. This is going to be the first opportunity for you to really show that you know how to focus in lab. So with that said, guys, you need a completely blank piece of paper. This is so complicated. All right. So guys, we're back to calorimetry. But now what we're doing is we are talking about calorimetry not the way the AP people want us to. We're talking about this like it really works. Remember we had Liam talking about the idea of perhaps isolation and insulation. We had Nora talking about the idea that maybe we simplify our surroundings because it's just the water that gets there first to absorb the energy. And guys, neither of those is right. Remember what we said in second period. The way that the AP authors justify this is there is a tagline at the end of the thing that says, assume that all the energy lost by the reaction is gained by the water. But we also talked about how we know in reality that's not the case. And how do we know? And we know because the stirring bar and the air and the thermometer are all in contact with the water, and they are also absorbing energy. But guys, we know that the story doesn't stop there, because if we know if we come back the next day, all of that energy is gone and it's bled into the room. So now, guys, we need to talk about the whole picture. I would encourage you to draw a smaller calorimeter, and that'll work, at the top of your paper. And now, guys, we're going to talk about the reality of what's going on. I kind of called Nathaniel out on this at the end of second period. And understand, I wasn't calling you out. I was just trying to make sure we understand this. Guys, there is the possibility that the energy doesn't go from the system to the surroundings, right? It could go from surroundings to system. What kind of reaction would that be? So for the conversation that we're going to have right now, we just need a way to talk. So we are going to talk like the reaction is exothermic, okay? In the lab we're doing Friday, it will be exothermic. But guys, in the lab that we're going to do to follow up on that, it could be endothermic. But let's talk exothermic. So guys, here's what we're going to do. Draw a little box.
I think that's fun.
Huh.
I think you might have gone into shapes.
I think I did.
Interesting.
I have to confess, I kind of like it. Let's try this again. So guys, with that said, here's what we want to do. Draw yourself a box, and that box is your system. Guys, you're going to, I know I sort of set you up like, oh, this is hard. Oh, no. You guys are going to love this. The logic behind this is fascinating. So guys, let's talk. Well, we understand, right? There's water in here. Maybe we should draw that too. So guys, we have already accounted for one place that the energy goes. Into the water. So, guys, let's refresh our memory on how that works. So we are going to call this path number 1. And guys, some of the energy goes into the water. How do we think about the energy going into the water? Well, guys, how do we know energy is going into the water? Temperature changes. So we simply say Q. Is it MC delta T? I want to do it the way you learned it. So guys, we can quantify the amount of energy that is going into the water by simply saying we can measure the amount of energy going into the water because we know its mass, its specific heat, is a constant. And then guys, we can measure its temperature change, and that represents some of the energy that's being released by the reaction. In AP, it represents all of the energy released by the reaction, but for real, it only represents part of it. So guys, call time out. This is what we established second period. Things there that you want to explore. Yeah.
Is there any even slight variation in the specific heat of a substance if you get different samples of it?
So long as it's distilled water, you're gold. Okay. And frankly, Adam, in this lab, we don't use distilled water. We're going to use tap water because there's so little mineral dissolved in. Well, there's a lot of mineral relatively in our tap water, but it's not enough to change the specific heat. Enough that our thermometers would feel the difference. So we're just going to use tap water. Okay. You guys settled on that? Here we go, y'all. Blinders are coming off. Where else does the energy go?
Into the cup.
Into the thermometer and the cup and everything else.
The air.
Guys, we're going to say that this energy, we're going to call this energy change 2. That is the energy lost to the calorimeter. So guys, what is the calorimeter? And we are going to say the calorimeter is everything inside of here that's not the water. Is that okay? So guys, energy change 2 is going to be the energy lost cal or m at So it's the energy lost to the calorimeter. And guys, that is simply going to be the cup and the koozie and the stirrer and the thermometer and even a little bit of air at the top and then the cardboard lid. Guys, that's the calorimeter. And energy will be lost to the calorimeter. But guys, that's not the end of the story. Where else does the energy go?
The air.
Into the room. We're going to call that energy change 3. And we're just going to call it the energy that's lost to the room. Now guys, let's establish some ideas. How do we know that energy is lost to the calorimeter? It has to be. It's all touching each other. Guys, how do we know that energy is lost to the room?
It has to be. It's all touching.
Go ahead, Dylan.
It's touching the calorimeter, which has energy given to it.
Yeah, there's a flow, right? But what evidence will we have?
The calorimeter.
Yeah, we come back and it'll eventually be room temperature, right? All right, now guys, this is where this gets crazy. We need to gather ourselves.
Sit down.
We're not going to sit down. Guys, how do we quantify 2 and 3? How do we measure the amount of energy that is gained by something as complicated as a calorimeter? Guys, we don't have the specific heat for a thermometer. We don't have the specific heat for the air gap. We don't have the specific heat for the cup or the koozie. How do we figure out how much energy is going into the calorimeter? And guys, I asked this hypothetically. Now, we'll talk in a minute, but that's a challenge. But then, guys, the even greater challenge is this. How do we measure the amount of energy that's going into the room? Yeah, don't go there. The answer is you don't know.
We don't.
And so when we do. But guys, the answers to this are brilliant. And we are going to tackle them one at a time. How do we tackle this? We tackle this via heat capacity. How do we tackle this? We tackle this through extrapolation. Now guys, here's the problem. You're going to understand the concepts because I'm good at explaining this. But understand, guys, it doesn't stop there. Because you've got to be able to take these ideas, and not only do you have to be able to think about these things mathematically, you've got to turn this into data charts. And guys, that's your homework for tonight. Okay. It's going to be to come in here on Friday with this lab parsed apart. And you'll notice I haven't even given it to you yet. You're not ready. Guys, you are going to need to figure out these procedures because the procedures in the lab address all of this. And then in addition to that, you've got to turn it into a data chart. So guys, pay attention. Let's talk about the heat capacity of the calorimeter first. So guys, I'm going to switch screens. You have room at the bottom of your paper, but I don't. So guys, it goes like this. That's our calorimeter. But guys, again, we can't, well, let's do this. When the reaction happens inside of the calorimeter, exothermic, what's going to happen to the temperature of the calorimeter? It's going to go up. Is that okay? Energy is going, the water's temperature goes up. So does the calorimeters. But now, guys, how can we measure the amount that the temperature of the calorimeter goes up? Well, let's talk about that. This is foundation. So guys, when we do this reaction, when we do this in lab, I forget which one we put in first, the acid or the base. It doesn't matter. Say that we put the acid in the calorimeter. So guys, we can measure the temperature of the acid, right? What's it going to be? Room temperature. And we can measure the temperature of the base. What's it going to be? Room temperature. And when we dump them together, did you guys notice this is where our water is coming from? Because the acid and the base are aqueous. So guys, when we dump these together, remember the water is not our system, it's a surrounding. So when we dump these together, the HCl's, I shouldn't have put base, I should have put NaOH, but we're okay. Guys, those are going to react together, right? And they're going to give off energy. Where does the energy go? A lot of it into the water. What happens to the temperature of the water? It goes up. So we can measure it before and we can measure it after, and then we know the change in temperature, right? But guys, some of that energy is going to go into the calorimeter. How can we measure how much the temperature of the calorimeter goes up? It's the same as the acid. So guys, think about it. We've got a calorimeter, and we're going to dump the acid into the calorimeter. What's the temperature of the acid? What's the temperature of the calorimeter? Room temp. They're all at room temperature. So when we put those together, when we measure the temperature of the acid, we're also measuring the temperature of the calorimeter. Does that make sense? Okay, now, we're going to carry out this reaction inside of the calorimeter, and we are then going to measure the temperature of the acid and base combined together. But what we're really doing is measuring the temperature of the water. So will that temperature be higher or lower than room temperature? Higher, because it's exothermic. So guys, by measuring both of those, we can figure out the temperature change for the water. Does that make sense? Mm-hmm. But does it also make sense that that's the temperature change for the calorimeter?
Yeah. Because.
Go ahead.
Okay, I just want to make sure I'm like understanding.
Yeah. No, these and guys, this is we need to do the I want to make sures.
Is it because, like, for at one point the water would be warmer than the calorimeter because it would absorb the heat.
Yeah, good.
But then the water would radiate into the calorimeter and it would all become just
one temperature. And actually, it's interesting. The glass and things like that absorb heat so readily that it's really appropriate. I love the way you're thinking, but it's appropriate to not think about it that way. It's not like energy goes out into the water and then it goes into the calorimeter. It all absorbs the energy simultaneously. But I love the way you're thinking. Go ahead.
And we can be sure that they'll be the same temperature because heat only transfers until it's the same heat.
Yes, not until it's the same heat, until it's the same temperature. Is that okay? Mm-hmm. Okay. So now, guys, we know the temperature change. This is subtle. Don't miss this. We know the temperature change of the water. And that allows us to do this math, right? But we also know the temperature change of the calorimeter. And guys, that temperature change, hear the words carefully, that temperature change is a function of the amount of energy that this calorimeter absorbed. Does that make sense? But guys, this is a really complicated system. The calorimeter is a complicated system. And because the calorimeter is a complicated system, we can't talk about its specific heat. We don't know the C value for a calorimeter. But now, guys, look back in your notes from second period. No, we're not even going to try to figure it out. We're going to use the heat. Reread the definition of heat capacity.
The amount of energy needed to raise a system's temperature.
A system's temperature 1 degree Celsius. So guys, if we knew the heat capacity of our calorimeter, remember our analogy, if we dump in 100 joules and if it goes up, did I say 5 degrees, 20 degrees, whatever. So if we know the heat capacity, and guys, think through this with me. If we know the heat capacity of the calorimeter, And if we know the temperature change of the calorimeter, we can figure out the amount of energy that the calorimeter gained. Think about it this way. If the heat capacity of the calorimeter is 20 joules per degree Celsius, and if the temperature of the calorimeter goes up 10 degrees, how much energy did it gain? 200 joules. Does that make sense? So guys, when you buy research grade calorimeters, thousands of dollars, they come to you calibrated. Here's calibration, right? They come to you calibrated. Stamped on the side of the calorimeter, it says heat capacity equals 25 joules per degree Celsius. So they come to you calibrated. But ours aren't calibrated. Why aren't they calibrated? Because they're made out of junk that's sitting in your drawer. So guys, you've got to figure out how to calibrate. This is hard. You've got to figure out how to calibrate your calorimeter. You've got to figure out how to calibrate your calorimeter. Now guys, when you're done with that, what will that look like? It will look like some number of joules per degree Celsius.
So,
Right. Guys, I want to give you a minute with the so. How could you do this? How could you calibrate your calorimeter so that you know it takes this many joules to raise the temperature a degree Celsius? Talk about it. How could you do it?
I just got the loaded wheels. I'm just looking at great.
Just spinning like that.
So is the specific heat, I mean, the capacity is the heat capacity the same thing as the capacity manager? Right, and then I got more.
We'll talk.
So when you have simulation, like the sheets out, so does it, like, because I know, like the water will like transfer like, so is the container that's we usually use like, I know like the example you have there is like a styrofoam,
Yeah.
so does it like, when it first happens, does it like, will like flow out from the water or just from the reaction itself?
From the reaction. All right, guys, join me. I'm not even going to ask you what you came up with because my experience has been it just creates confusion, and this is hard enough as it is. So guys, let's talk. When we calibrated our thermometers, what did we need? 2 fixed points. Guys, when we calibrated our pipette, what did we need? Fixed points, right? So guys, we need a fixed point. We only need one. We could do this multiple times, but one's good enough. Guys, which one of these two variables is going to be our fixed point? And the answer is the energy. Guys, what we're going to do is we are going to build our calorimeter, and then we are going to dump a known amount of energy into the calorimeter. What are we going to measure? It's temperature change. See this? We are going to dump a known amount of energy into the calorimeter. We're going to measure its temperature change. And if we dump 100 joules of energy in, and if its temperature change is 25 degrees, what's the heat capacity of the calorimeter? 4
degrees Celsius.
You get it? So now this gets even harder. Guys, how are we going to dump a fixed amount of energy into the calorimeter? Guys, this is brilliant. You ready? Follow my hands. Let's say 100 grams. This is 100 grams of hot water. Let's just use easy numbers, 100. This is 100 grams of 100 Celsius degree water. This is 100 grams of 20 degrees Celsius water. When you dump them together, what happens to the hot water? It cools down. What happens to the cool water? It warms up. So guys, again, equal masses, 100 grams, doesn't matter, equal masses. If this is 100, and this is 20, when you mix them together, what will the temperature be? 60. The average. Good? But guys, when you do this in the calorimeter, the temperature will not be the average. Watch my hands again. What you're going to do, and again, we're using easy numbers. 100 degree water, 20 degree water, you're going to dump them together in the calorimeter, and it's not going to be 60, it's going to be less than 60. Where did the energy go? Into the calorimeter, huh? So now, guys, the idea is this. I would encourage you to write this down. In a perfect world, the Q lost by the hot water will be equal to the Q gained by the cold water. But guys, that is not what is going to happen. The heat that is lost by the hot water is equal to the Q that is gained by the cold water and the Q that is gained by the calorimeter. So guys, what is this going to look like? Well, what we're going to do in lab is we are going to take hot water and cold water, same masses to make the math easier, and you're going to dump them together. And guys, when you do this, what should the temperature be?
The average.
No.
Or lower.
Lower than the average. And then, guys, the math is eventually going to look like this. This will be MC delta T for the hot water. This will be MC delta T for the cold water. And we are going to solve for Q. But guys, if you screw this up in lab, you're doing the lab over. Follow my hands again. Hot water. You need a minute to write this down. Hot water, cold water, 120, 120. When they mix together, where will the temperature end up? Below the average. Guys, when you do this, for some of you, your temperature is going to end up above the average. You made a mistake. But guys, if you don't catch that mistake, you are going to do the remainder of the lab and in a calorimeter that is impossible to calibrate. Because in your literal world, your calorimeter gives off heat. It doesn't absorb it. And guys, I'm not going to stop you. And you're going to continue through the lab, and you're going to sit down to do your calculations, and you're going to go, oh crap. And then you're going to come in and do the lab over. So guys, there's a term for how to avoid this. This is a slang term, but you'll hear it all the time in college. Back of napkin calculations. You'll hear your professors talk about this all the time. They're called back of napkin calculations. And literally what you're going to do is you're going to grab a scrap piece of paper. You're going to throw it out when you're done. And guys, you're going to grab a scrap piece of paper, and given the temperatures of your actual hot and cold water, you're going to figure out the average. And then, guys, what are you going to do? Make sure that the temperature that you end up with when you mix the hot and cold water is below that average. What if it's not? You're going to do it over. But now, guys, with all of that said, this then allows us to figure out Q. So we figure out the energy that was lost by the hot water, gained by the cold water. And then, guys, by the way, which number should be bigger?
Lost.
The energy lost, because some of the energy is gained by the water and some of it by the calorimeter. And guys, you're going to do this math, and that'll allow you to solve for Q in joules. But then, guys, in order to come up with this, which is joules per Celsius degree, you need to know the temperature change for the calorimeter. How do you measure? As is the same as the temperature change for the cold water. So guys, what you're going to do is in this calorimeter, when you calibrate your calorimeter, guys, what you're going to do is you're going to put the cold water in the calorimeter, and when you measure the temperature of that, you're actually measuring the temperature of the cold water and the temperature of the calorimeter. Then you're going to dump in the hot water, and then you're going to stir this, let it come to equilibrium. Then you're going to measure the temperature of that, which is not only the temperature of the mixture, it's also the temperature for the calorimeter. Does that make sense? Go ahead, John.
How long do you have to wait for it to become like equilibrium?
Great question. And the answer is, first of all, John's question was, how long do you need to wait? And guys, the answer is, first of all, hello? Hello? I was pushing the volume. Guys, is this too loud? Okay. So the answer is, first of all, the answer assumes that you're stirring. If you're not stirring, it doesn't work. But then the answer is when the temperature stops changing. So what you're going to do is you're going to read the temperature and you're going to go, okay, it stopped changing. You'll see in the lab, but when it stops changing. Go ahead.
Why is it that we can't pour hot water by itself into the calorimeter and measure the amount of heat it lost and call that the amount that the calorimeter gains?
So you could, but we get greater accuracy with greater mass. By having a heat sink there to absorb the energy, we actually end up with better results. So in theory, you could dump the water in there, and you could measure how much the temperature drops, and that's the energy lost to the calorimeter. But this provides better, more accurate results. Go ahead.
Do we use our calibration curve?
That's an interesting question. I'm really glad you brought this up. Guys, do we need our calibration curves? We don't. Why not?
Because it's by subtraction, so the error will be accounted for.
Yeah, guys, never are we measuring, let me say that, we're measuring temperatures, but what are we using those temperatures to arrive at? Temperature changes. And the idea is that our calibration curves are linear, meaning that the temperature, the error is consistent throughout the curve, which means, as you said, the error subtracts out of our measurements. So guys, anytime we're doing temperature change, we don't need to adjust for the calibration of our thermometers. You guys good? Yeah.
So it's about like the I mean, it's like a different way to say it, but it's like the difference between 2 points
Yeah.
on the curve
Uh-huh.
as opposed to the actual points themselves.
Exactly. That's exactly right. You guys okay? All right. You ready to tackle number 3? Where'd it go? Did I go by it? Oh. I must have clicked right past it. Right there. Guys, this one is cool. I frankly, degree in chemistry, right? When I was doing calorimetry my sophomore year in college, we stopped at this. I learned this when I started teaching AP, and this is brilliant. You ready? So guys, number 3 is how do we account for the energy that goes into the room? So guys, let's go forward. New screen. This is number 3. How do we account for the energy that is lost to the room? You ready? This is really good. So draw yourself another calorimeter. Just to be consistent, although I frankly don't remember, did we put the acid? We put the acid in here, right?
Yeah.
All right. And guys, this is a magic lid that we can pour sodium hydroxide through.
Whoa.
All right. So guys, here we go. Again, following my hands. Here is the temperature of the acid, which is also the temperature of what? The calorimeter. Now guys, how will the temperature of the base compare to the temperature of the acid?
It'll be the same.
Be the same. Guys, watch my hands. This is not hot and cold. This isn't cold stuff and hot stuff. Guys, what we've got when we do the reactions is we've got room temperature acid and room temperature base, right? They're the same. But now guys, watch my hands. Okay. Guys, watch my hands. So when we mix these together, this is loud. Guys, when we mix these together, what happens to the temperature? It goes up. Yes? So guys, where does the energy go? Some of the energy goes into the water. Some of the energy goes into the calorimeter. But now guys, watch my hands. Starting over. Room temperature acid, room temperature water. Mix them together. Bunch of energy goes, this is temperature. Energy temperature goes into the calorimeter in the water. But then guys, over the next 24 hours, what's going to happen to the temperature? It's going to drop. Where's the energy going? Into the room. But now guys, the question is this. When we mix the acid and the base together and the temperature initially goes up, does it just hang out up there and then 10 minutes later it starts to drop? And the answer is no. Guys, the energy is bleeding into the room the instant energy is released. So seriously, guys, it's mixing together. Boom, temperature goes up. But even as the temperature is going up, energy is being lost to the room. Does that make sense? So guys, now the question becomes, how do we measure that amount of energy? Guys, check this out. Draw this with me. This is brilliant. I'm going to get rid of the calorimeter so we have more room. Guys, draw a graph. Your y-axis is time. And this is temperature. Now guys, pay close attention. You are going to create a 0 point in time that is not the origin of the graph. So what is everything to the left of this line?
Negative.
Before the reaction happens. Okay? Then guys, when you carry out your acid-base neutralizations, this is the data that you're going to collect. Remember, stirring all the while, right? And so you are going to measure the temperature of the acid inside the calorimeter. And guys, that will be the temperature before the reaction starts. What will the temperature of the base be as well? The same. But then guys, when you mix these together, what's your graph going to look like? Well guys, we're going to assume that the temperature is constant, and it is, it's room temperature, until you dump these together. And then guys, what are you going to see? You're going to see the temperature go, woohoo! Where is that energy coming from?
Reaction.
The reaction. But then guys, you're going to collect data long enough that you're going to see this temperature begin to drop. Where is the energy going as the temperature drops? Into the room. But now guys, watch this. We've already established this idea. Does the energy start bleeding into the room a couple minutes after the react? It's right from the start, right? So guys, here's what you're going to do. Once you've drawn this graph, you are going to take a straight edge and you are going to extrapolate this line backwards. Let me keep going. You're going to extrapolate this line backwards. Then you are going to carry this line up from 0. Guys, what does that point represent? The temperature that the reaction would jump to had it not lost energy to the surroundings.
Okay.
Let that soak in. Guys, that temperature, which I have circled on the board, represents the temperature at time 0. It represents the temperature the instant these are reacted together. And what it does is it compensates for the fact that the reaction's temperature is going down even as it's going up. So what do we do with this information? Well, guys, this temperature becomes our final temperature. And this temperature becomes our change in temperature for all the math that we're going to do for parts 1 and 2. Right? So guys, this is the complexity and the brilliance of how we're going to do this lab. So we have a few minutes. Let's entertain questions.
So the change in T that you're having, so that's the change in T that you're gonna plug in for the second?
Well, let's talk. So where do we go with this delta T? Well, let's go back here. So where does delta T go into this? Well, it doesn't. Because this is our calibration. So where does delta T go into here? So first of all, that delta T will be the delta T for the that the water gained. Because that's, so remember, be careful here. So this is acid base, right? So where's the water? The acid and base are dissolved in them. Is that okay? So this delta T will be the delta T that is the change in temperature of the water. Okay? But now over here, we have, guys, how did we say we're going to abbreviate heat capacity? H sub C. So guys, H sub C is equal to Q over delta T. That's also going to be our delta T there. So that will be our delta T for both of those.
So then we're using, for that, we're using the Q that we got from the, equate, like, the, never mind.
No, so here Nora, I fear I may have confused you. So, first of all, we've got to talk about calibrating our heat, our calorimetry. That's different. But imagine this. So once we've done the calibration, let's just say 100 joules per Celsius. Okay? So now we know the heat capacity of the calorimeter. So what we can then say in calculation number 2 is this. So when we then use our calibrated calorimeter, our heat capacity would be 100 joules per Celsius degree. And so then our energy would be what we're solving for, and our C is our change in temperature, which would be that distance on the graph. Is that okay? And we'll play with it as we do calculations. Yeah.
So the gas at the top of the calorimeter counts as a part of the calorimeter system.
Yeah.
So does that mean that we would like to make sure that the final mass of the hot and cold water we're mixing is as close to the mass of the water that we're going to be carrying out our reaction in, so that the gas is the same?
So in theory, that would be best. To be honest with you, I haven't reread this lab since last year. But realize we're going to have, so the masses are, so in our calibration step, the masses will be the sum of the hot and cold water.
Mm-hmm.
And then in our acid-base neutralizations, our masses will be the masses of the acid and the base. But what we're really measuring is their volumes, and assuming it's 1 gram per milliliter. I don't know that those are the same, but it's not enough to change the results. Go ahead, Nathaniel.
So I've got kind of 2 questions. When you said that we can work backwards from that straight line, does that mean that the heat is leaving at a constant rate?
Yes, that's exactly what that means. Good.
And then just to make sure that I'm comprehending what this is doing. So for the room 1, we're not getting another amount of heat that's left.
What's the room 1?
I mean for calculating
the
heat that's leaving the room, we're not getting another amount of heat.
No, yes, thank you. So here, it's not like a third calculation. what it is a better way to come up with delta T.
We're pretending.
And that delta T then populates these equations.
So for that one, we're changing the numbers, and then for like the calorimeter one, we're finding the lost energy.
What do you mean changing the numbers?
Well, like extrapolating to find out what the numbers actually should be if the world wasn't a chaotic and strange place.
Can we not say numbers and can we just say temperature change?
Temperatures, yes.
So we're extrapolating to find the temperature change. What the temperature change should be if our system were perfectly insulated. And then we're taking that change in temperature to be the change in temperature for the calorimeter calc and the water calc. Is that okay?
Yes.
John, go ahead.
I thought the calorimeter calculations was for like boiling water.
It is, and that was, did you hear Nora say the first time or the, so the first thing we're gonna do with the calorimeter is we're going to calibrate it, okay? So we're gonna calibrate the calorimeter first, and that's gonna be our hot and cold water. Then after we calibrate it, then we're going to use that calibration, and we are going to know the heat capacity, that's the calibrated number, and then by knowing the temperature change, we can figure out the number of joules. Go ahead.
So we find the heat capacity of the calorimeter by using the temperature that was less than the average.
The hot and cold water and the temperature that's less than the average, yes.
Okay.
Yeah.
So what would you do with the? Oh, it would be the average subtracted by the.
Yes. James. Piper.
So I just wanted to make sure. So the order we're gonna do like the calorimeter, calorimeter, and then are we gonna figure out like the room part, and then figure out like the first.
Okay, so the order is going to be, we are going to calibrate the calorimeter. That will be the hot and cold water gain.
Yeah.
Okay. Then once we have the calorimeter calibrated, we will do the acid-base chemistry. And when we do the acid-base chemistry, we are going to be collecting time and temperature data. From that time and temperature data, we will then generate this graph. This graph will then give us our delta T. That delta T will then be the delta T that we will plug in here and here, and that will give us the energies that the reactions released as they were taking place. Just a second, James. Just a second.
For the calorimeter calculation,
Yep.
you said that it would end up being the same temperature as the acid and water, or like with the reactions, the calorimeter.
Sorry, say that again.
That like the calorimeter is supposed to have the same temperature as the water, like initially.
Correct. Yep. So what we're going to do, so imagine your calorimeter, and in the calibration, it will have the cold water in it. In the acid-base reactions, it has, I think, the acid. I'm not sure, but whatever that is, whether it's just water or whether it's an acid, we can measure the temperature of the calorimeter by measuring the temperature of the liquid that's in it.
Okay.
Is that okay?
Yeah.
Okay, go ahead.
How does the heat capacity of the calorimeter play in?
So the heat capacity, so let's talk about all the things heat capacity of the calorimeter. So the first thing we're going to do is we're going to establish the heat capacity of the calorimeter by mixing hot and cold water inside of there. And when we mix hot and cold water inside of there, the hot loses energy to the cold, but the hot also loses energy to the calorimeter. And if we know the difference, say that the hot water lost 100 joules of energy, but the cold water only gained 90 joules of energy. So how much energy went into the calorimeter? 10 joules. But if that 10 joules of energy caused the calorimeter's temperature to go up 5 degrees, we now know the heat capacity of the calorimeter, 2 joules per degree Celsius. So if 10 joules made it go up 5, 10 divided by 5 is 2. So that means every 2 joules of energy that the calorimeter gains, its temperature would go up 1 degree. Once we've then established that, so now we know our calorimeter has a heat capacity of 2 joules per degree Celsius. Then imagine we do the acid-base reaction in there, and the temperature of the calorimeter goes up 30 degrees. Well, what would cause this temperature to go up 30 degrees? 60 joules of energy, and that's how we'll work that.
And then the temperature of the calorimeter is just the temperature of whatever's inside of it.
Correct, before and after, and that is what this lets us figure out.
Okay.
Amazing questions, y'all. Go.
Okay.
James.
So to find the like rate that it's going down, are we just gonna watch it for a bit and see? So
When you say rate going down, you mean this?
yeah.
Yeah, so not watch it. What you're going to do is you're going to stand there with a stopwatch. And I think it's every 30 seconds, I don't remember. But you're going to just start, it may be faster, maybe 20, 10 seconds. You're just going to start writing down the temperature over time.
Okay.
And you're going to see that temperature go down over time because energy is going out into the room.
And that'll allow you
Uh-huh.
to. And so pretty much you're going to use a stopwatch the whole time to see,
Yeah.
okay, when does it reach its peak?
Yeah.
Type thing?
Yeah,
So
exactly.
that'll be your time.
Exactly. Well, so what you're going to see is times 0. So
Yeah.
we're coming into time 0 and everything's room temperature.
Yeah.
And we mix them together and temperature goes woohoo!
Yeah.
Because the reaction's giving energy to everything, the water, the room, the calorimeter.
Yeah.
And then, so you're going to see over like the first couple readings, your temperature's going to go up, go up, go up, go up. And that's represented by this sloped line as energy is moving out of the reactants and into everything. But then once you hit that peak, then you're going to see the temperature go down. But understand that peak does not actually represent all of the energy from the reaction heating everything up, because that peak is a little lower than it should because energy is going into the room. And that's when we extrapolate. Back.
Okay.
Yeah, James.
So do we have to do extrapolation first? Because so since the delta t is in the other equations and we figure out delta t with this, we have to do extrapolation first.
Yes.
And then
Correct.
we use that variable to get to those.
Exactly. Yeah, that's right. Go ahead. Just a second. Go ahead.
Okay, so in the end, when we're doing calculations, the like net sum
Good.
of the
Yeah.
energy is going to be our change in temperature in the water, and then the change in temperature in the
Calorimeter,
but not the room, because we already accounted for that.
Exactly, yes. And that was kind of, somebody was asking about, Nathaniel, was it you, about does calculation number 3 give us another amount?
Yeah.
And the answer, so you've done a great job of summarizing this. So the idea is that we will have a number from here, and we will have a number from here, and eventually we will add those up. The amount of energy that we have to keep track of because of the energy going into the room is actually contained in both of these calculations because we use the actual delta T. Nathaniel, did that work? Is that, okay, go.
All right, another couple of questions.
Please.
Do we need to do the whole room extrapolation process when we calibrate the calorimeter?
We actually will, and I neglected to mention that, but guys, we will actually be collecting temperature data over time for the calibration, because it makes sense, right? That same calorimeter that bleeds energy to the room when we're doing acid-base also bleeds energy into the room when we're mixing hot and cold.
And the other thing was for like extrapolating that graph back to time 0.
Yeah.
How do we know when time 0 is?
It's the moment you dump the reactants and products together.
So like we'll start the stopwatch right when they go together, and then we're at how much time?
That's right. Yeah, go ahead.
Okay, just making sure I understand this. But so the room temperature, we have the little calorimeter.
Are we
temperature.
calibrating or are we acid basing?
That'd probably be for acid.
Okay, keep going.
So we have the calorimeter temperature with the water temperature,
Mm-hmm.
and then those temperatures are slowly released and getting smaller over time into the room.
Correct. That's right.
Okay.
Yep, that's right.
So the room temperature is the overall temperature, which is
Yes.
the change in T.
That's right.
Okay.
Now, guys, but I should say this. This is maybe a little anticlimactic. So think about this. Eventually, where is this line going to end up?
Temperature.
I mean, forgive me, I can't do it, but it's like down, it's back to room temperature, right? Which if we were to follow the slope would be all the way out here somewhere, yeah? So guys, what we're talking about is this thing bleeding all of that energy back into the room over the course of half a day. So the slope of that line is frankly wildly disappointing. It's actually probably more like this, like that's even going up.
The room is
heating
up.
We put our reaction in an oven.
Well, no, because remember the temperature in the classrooms when we first came back from summer?
Yeah, that's true.
Yeah, how Coxon's room was like 900 degrees.
That's because AC.
That's my point. So in that setting, never mind. Okay, so guys, don't expect huge declines, but understand that if you don't get huge declines, what that actually means is this point and that point will not be wildly different, but they will be different.
Just a little.
Just a little. Okay. So guys, here's where we are. Came into this, hey guys, this is hard, this is deep. And I absolutely love the conversations that we've had. I mean, I think for some of you, you've probably even forgotten that your butt is numb. Right? Maybe? I don't know. I don't know. Now you know. So guys, here's what we're going to do. These conversations have been so rich and so good that what I don't want to do is I don't want to send you out the door and throw you to the dogs. What I want to do is I want us to be together when we start putting our data charts together. I want you to be here so that you can do it in a supported environment because I know there are different levels of comfort with the conversations we just had, and I don't want you to walk out of here and get home and try to turn all of this into a data chart and then have yourself go, oh crap. So guys, what I'm saying is I don't want to turn this into homework. Yeah, oh yeah, plenty of, and this is especially bad. We're not going to use it, of course. But guys, what I would like to do is I'd like to give you the lab handout. And I'd like to talk you through it.
So on the test that we take, is it going to be the AP stuff or all the college stuff too?
No, so good question.
Or is this just
What the last hour you will not see even on our unit tests.
Thank goodness, I would fail. Actually, I'm going to fail. Sorry.
I would say like 15 seconds. Of course.
Okay, guys, grab these and give them a 30,000-foot skim.
Where's procedure? Oh, there it is.
Oh, procedure's over here. Procedure and seizure, the main two parts of the lab.
Oh, yes, the largest board.
Where's the seizure? Seizure's back here.
I see 30,000 foot seats.
So guys, now that you've had a chance to page through it, join me on what we'll call page 1, and let's go through this together. So guys, you'll notice the chemicals as advertised. Notice they're all 1 molar solutions. Hydrochloric acid, acetic acid, and sodium hydroxide. Guys, for the purposes of this lab, we are going to assume, wait a minute, I should be careful about this.
Assume something after spending all this time making sure it's actually.
No. So guys, for this lab, we are going to assume that the densities of these acids and the base, we're going to assume the densities of these are 1 gram per milliliter. What is that the density of? Water. So we are going to assume that the densities of these solutions are 1 gram per milliliter. As a result, we will be measuring milliliters, but we can count those as the mass in grams. Yes? Okay. So then, guys, turning the page. This is closer to what our calorimeters are going to look like. Except for instead of standing this in a 400 milliliter beaker, it will be 1 styrofoam cup nested inside of a koozie. Then guys, if you want, I would encourage you not to, but if you want to read over all of the math on the next few pages, you can. I would suggest you don't. Then turning over the page again, 322. First thing we're going to do, guys, is we're going to find the heat capacity of the calorimeter. I love that Piper was asking earlier, what order are we going to do this in? Guys, this is the order. The first thing we're going to do is we're going to calibrate our calorimeter. Guys, notice that we're going to use 50 milliliters of room temperature water, tap water. Again, not distilled water. It works well enough. And then, guys, in the third paragraph, place exactly 50 milliliters of water into a dry beaker, heat it over a low flame until it's 20 degrees above room temperature. Guys, not 15. 20 is better. Even 25 is okay. Yeah. Notice it says do not heat to boiling, which is strange because you're only going 20 degrees up, but. Then, guys, notice it says pour them as completely as possible, replace the lid, carefully stir, observe the temperature for the next 3 minutes, and record the temperature every 15 seconds. Yes? So, guys, turn back to your data chart, which is conveniently located on 327. And notice what it says, column A, heat capacity of the calorimeter. Time ranges from 0 to 180, which is 3 minutes if you're doing, you got the idea. And then, guys, notice you have columns where you'll do the same thing for the neutralization reactions, as we said, temperature over time. Okay, then going back, what are you going to do when you are done with, well, how are you going to know if your data from part A is valid? You're going to do your back of napkin calculation. If you don't think you're going to remember, I would write something down next to that that says back of napkin calculation. Now, guys, notice beneath that, it then goes on to part B. Here you're using 50 milliliters of sodium hydroxide. Oh, I had it backwards. The sodium hydroxide goes in the calorimeter, and then you'll add the acid later. Doesn't matter.
It doesn't really matter.
It doesn't matter at all. No, although the thing that might be helpful is that the sodium hydroxide is the consistent between the constant between the two trials. Because in trial 1 it's sodium hydroxide and HCl, the other is sodium hydroxide and acetic acid. Maybe it helps to keep that consistent. And I think we're good there. Notice down below the graph. Guys, frankly, this is more indicative of the slope of that line. I know, right?
Slope?
Yeah, it's you'll see.
There's
Yeah.
a slope.
It says are the styrofoam cups just gonna dry off? Like, cause it says dry the
Yeah, so just paper towel them out. That'll be good enough. Yeah, because think about it. Eventually what you're doing is you're going to put more water in, right?
Yeah.
So you just don't want a puddle of water in the bottom of that would appreciably change the volume. So then, guys, you'll continue this again, and you'll do it with acetic acid and sodium hydroxide. We okay? Okay. So, guys, this is what we are going to do in the place of we'll put our data charts together on Friday. Your homework is now the pre-lab. So, guys, for the pre-lab, we are going to do number 1. You're going to do number 3. You're going to do 4 and 5. And 10. Now, guys, turning your attention to question 10, this is another way that the AP authors will fudge their way out of having to do all the additional math. Reading that sentence at the very bottom of the page, it says, assume that it's a perfect calorimeter. That means, guys, that it doesn't absorb energy. Therefore, where does all the energy go? Straight into the water. And that the specific heat of the solution is the same as that of pure water. It just means you use 4.18 as the specific heat of the water. So guys, that's your homework for Friday. You are going to come in with those, and that's it, nothing in second period. So guys, you're going to come in with those questions done. We will turn those in. We will pull our data charts together. And guys, we have about 5 minutes. We'll pull our data charts together, and then we may go into lab and at least pick our bits to figure out which things we're going to build our calorimeters out of. We might even have time to calibrate our calorimeter. But guys, the other thing that I'm going to ask you to do for quote-unquote homework is at least reread the procedures so that you have a really solid sense of how this is going to work when we get in the lab. So guys, you ready for a mind-numbing piece of data? We just talked about calorimetry for 1 hour, 45 minutes.
We just made a feature-length film about.
We did.